Now we are here. Yeah. Last time we derived this formula. Okay. Size reduction. The purpose for this formula, we want to reduce the problem size. That's the goal. Yeah. So here you can see, in problem solving, size reduction is a pretty common strategy people use to solve the problem. Yeah. So here we take that strategy, and how did we get this formula? Yeah. Based on one important theorem, yeah, in number theory, right? In number theory. So it's called a division algorithm. So it's a very simple, very fundamental, but very important in numbers theory. So division algorithm, integer division with quotient and a remainder. Remainder. Here we need to use remainder. Yeah. All right. So now the size reduction. Yeah. Here, when we talk about size reduction, before we go to the next step, I like to talk about the meaning of size. But here I do not want to go too far, just a little bit. Yeah. The problem size, right? Yeah. The problem size, currently we have two different meanings, right? Yeah. The first one regarding the array input. If our input comes from an array, in this situation, that the meaning of size is the number of elements in the array. But there is another meaning. Yeah. So our input is just one number, one integer. Yeah. This case, it's the magnitude. Yeah. Magnitude. Yeah. Yeah. So it's different. Magnitude. The example is prime factorization, right? Yeah. So we have a good example for this case. Prime factorization. All right? Yeah. But here, if I ask you, what's the meaning of the problem size? Because here, there are two input numbers, m and n. Yeah? Two, not one. If one is easy, the magnitude, right? Two, the magnitude of which one, right? Yeah. So in this case, there are two numbers. Yeah. Yeah. So many times, yeah, in our problems, many times, for some concept, like this situation, yeah, people may not have a clear definition of the prime size. Yeah. May not have a, definition. So all the problem solvers agree on. Yeah. So the situation like this. So what's the specific problem size here? Yeah. So there are many different ways people can define. Yeah. Sometimes, because any definition, there must be the first person to define it, right? Yeah, after the first person define it, then all other people need to agree on this definition. Then people use it. Yeah. So for this case, there are several possible ways people can define. One is use the maximum. Yeah? So maximum of m and n to define the problem size. Yeah. But how about there is another way to define m plus n to be the size? How about that? Right? Also reasonable, right? Yeah. The magnitude, sum of the magnitudes of two given integers, two non-negative integers, right? Also reasonable. Yeah. Yeah, yeah, things like that. Okay, all right. Yeah, but here it's not important, right? Yeah, because any of the definition, first one, second one, this formula reduces the problem size without any question. Yeah. Yeah. All right, so let's go to the next step. Yeah. Now we apply this formula, our key formula, to solve this GCD problem. Yeah. All right. It's called the Euclid's algorithm. Yeah. More than 2,000 years old. Yeah. So this algorithm is very old, more than 2,000 years old. Yeah. Yeah. Published in the book, Euclid wrote a famous book just called Books, a volume of sequence of books. Yeah. All right. It's like this. The rule. Yeah. Our recursion rule. Two base cases. Yeah. Then the general case. To calculate GCD of x and y, first you check if y equals 0, the base case. If y equals 0, yeah, you need to make sure x not equal to 0. Yeah, yeah, because in our condition, not both 0, right? Yeah. So in the given question, we require m and m. There is a condition here. Oops, sorry. Not both 0. That's a condition. Okay? All right. So we need to make sure x not equal to 0. Otherwise, if x equals 0, your function should return an error message that says there is no greatest common divisor between m and n, or x and y. Okay? All right? Yeah. So if x not equal to 0, then this function returns x. Yeah, the first base case. Then the second base case. Yeah, there is a second base case. Second base is x mod y. This percent sign, modular operation, mod. Okay? Yeah? After modular operation, you take the remainder. X, you do integer division with y as the divisor, but you do not take the quotient. You take the remainder. That's the modular operation. If the remainder equals 0, what's the meaning of it? The meaning is x is an integer multiple of y. If x integer multiple of y, greatest common divisor must be y. Yeah. So that's our second base case. All right? So other than these two base cases, now our general case. General case, then we apply our key formula, main formula. Okay? Yeah. Size reduction formula. Yeah. Recursion. Size reduction formula. Yeah. That's the Euclidean algorithm. Yeah. All right. Yeah. Then, so after we complete, this is the solution. After we complete this solution, yeah, we need to make some conclusion. Yeah. Several things we need to discuss here. The first thing, simple. Why we do not allow both m and n to be 0? Is there any problem? If both 0, is there any problem? Why we say GCD does not exist if both 0? Can you see that? Yeah? Oh, yeah. Yeah. I hope everyone can see it. Yeah. Here, GCD, greatest common divisor, right? Yeah. So here, let's look at the divisor of 0. Let's look at this question. What are those numbers that can be used as divisors of 0? Okay? Yeah. Can 1 be the divisor of 0? Is 0 an integer multiple of 1? 0 multiple of 1, right? 0 is an integer, right? Yeah. So 1 is a divisor, right? Is a divisor. How about 2? Divisor. How about 3? So any integer is a divisor of 0, right? Yeah. Now you tell me, which one is the greatest divisor? There is no greatest divisor. There is no greatest divisor. Yeah? Yeah. All right. Based on this observation, now you can see why we do not require both 0. Yeah. If one of the two numbers, if you have one is 0, one non-zero, that's easy. That non-zero number, that's the greatest divisor. Yeah, because it is a divisor of 0. It is also a divisor of itself, so you get a greatest divisor, common divisor. But if both 0, you can never get greatest common divisor. Okay? 1 million is a common divisor. 1 billion also common divisor. 1 trillion also common divisor. Which one is the greatest? No greatest. Yeah, so that's why we do not allow both integers to be 0. Yeah, that's the first thing. Yeah. Second thing, why this algorithm runs much faster than the prime factorization based algorithm. Prime factorization, yeah, we know prime factorization is very slow. Here, why in this algorithm we can avoid prime factorization? Yeah, here you can see what do we do? We just do integer division, right? Integer division or modulation. Yeah. That kind of operation, if you do this kind of operation in computer, extremely fast. Extremely fast. Okay? So our powerful computer, you can much faster than prime factorization. Yeah. Yeah. Right? Yeah? So here you can see, yeah, that's the reason. This one, even you apply this GCD algorithm on 2 huge integers, 1,000-digit integers, still very fast. 1,000-digit integers. Yeah? Yeah? Yeah. So now you get an idea. Yeah. Yeah. So this one is much better. Yeah, is the one we should use in the real world applications. Yeah. All right, so now we complete the part B. Next, let us move to part C. Fibonacci numbers. Another good example for recursion. Yeah. C.1, Introduction to Fibonacci numbers. First, we look at the problem. Our problem number 10. Calculate Fibonacci numbers. Yeah. Yeah. Given recursion formula, the formula given, so you do not need to derive it. Yeah. It's a very simple formula. 2 base cases. F0 equals 1, F1 equals, equals 0, F1 equals 1. Then you apply the recursive formula f sub n equals f sub n minus 1 plus f sub n minus 2 for n greater or equal to 2. Yeah. So simple. Yeah. All right. Question. Find the Fibonacci numbers n, f sub n. So given any integer n, now you need to calculate. Yeah. It's so easy, right? You can write a program, calculate this recursive function to find the answer quickly. Yeah. But the question is, how good is this algorithm? Is this algorithm acceptable for the consideration in our real world applications? So we need to answer this question. If it's bad, why it is bad? Right? We need to understand why it is bad. Yeah. All right, so let's look at that question. Yeah, so first, the first few Fibonacci numbers. Yeah. Yeah. Then, now, so we need to study Fibonacci numbers. Look at our plan here. Yeah. There are two ways we want to work on Fibonacci numbers. The first way, solve it algorithmically. So we want to develop efficient algorithm to find a solution. That's the first approach. Yeah. The second approach, different approach. Yeah. All right. So later we will use several methods to calculate Fibonacci numbers. Yeah. The second approach, solve it mathematically. Yeah. Yeah. So last time when we did that counting binary digits, that problem, yeah, I said, if we can find a recurrence relation, if we can solve the recurrence relation by a math formula, then that's the fastest way to calculate it. Yeah? You plug in the formula, you do the calculation using the formula. That's the fastest way. Here, the same thing. If we can find a math formula for the Fibonacci numbers, then if we use the formula to calculate it, that's the fastest way. Yeah. So that's our second approach. We want to discover a math formula for the Fibonacci numbers. Yeah. So these two approaches. Yeah. All right. Yeah. The first one, now let's work on the first approach. Yeah. Yeah. You write a computer program to do the calculation. Yeah. So this is let's say brute force method. Yeah. So we just apply, call the recursive function directly without any preparation, any special treatment. No special treatment. Okay? Yeah? We just apply the given formula directly. See? Yeah. So 3 lines inside the function, we only do the 3 lines. The first 2 lines are for the base cases, 2 base cases. Then the main calculation line, the third line. Then we're done. All right? And we are pretty constant. We are pretty confident here. We are very confident here, and this function is correct. Yeah. Yeah. So the result calculated by this recursive function must be correct. Yeah. That's no problem. Yeah. But other than the correctness, then for our computer science people, we need to study the efficiency of this function. Is it efficient? Is this function, this algorithm, brute force algorithm, efficient? Yeah, probably not. Yeah, but Now we need to see why it's not efficient. Yeah, that's important. Why it is not efficient. Yeah. All right. All right. Yeah. First, before I go to that one, why it is not efficient. Yeah. Let me give you some experiment result. Why it is not efficient. Okay. All right. Yeah. Yeah. Another thing is we just complete our first programming project, right? Yeah. Now we need to do the preparation for our second programming project. This topic for our second programming project. Okay? All right. Yeah. So we need to calculate Fibonacci numbers efficiently. Yeah. So that's the topic of the second programming project. Yeah. Here, let me give you some simple experiment results. Yeah. In the experiments, in the second project, you will do it by yourselves. Yeah. Here, I just based on the history experience. Yeah. Yeah. Experiments. Yeah. For this brute force. Okay. All right. Yeah. All right. Okay. If you apply this algorithm directly, when you calculate f of F45, it should not be a large input number, right? The input number is 45, pretty small. But if you calculate using the brute force method, it's very slow. Very slow. Okay? Yeah? How slow? If you compare it with your polynomial, our first project, calculating polynomial, because calculating polynomial for the brute force method, when I set 2 seconds, many students feel that's too long. Many students told me, so because I need to work on very large input number to get a response time 2 seconds. That's true. This one, if you compare with that, need dozens of seconds. Okay, based on your computer power. Okay, how fast is your computer? So you may need the possibility like 20 seconds, 30 seconds, 40 seconds. Based on your computing power. But in that level, in that level, that's very slow, right? But F45 is so small. The number is so small. Okay? Another thing is overflow. Because when you do the calculation, if you use long integer, then you may get overflow, right? So here, that line is, if you calculate F92, that's the last one before the overflow when you use long integer. Okay? All right. But if you calculate F93, then you get overflow. So you get an idea how large it is. Not too large, right? Because the overflow, that range is not very, for long integer, not very, 64-bit. Long integer 2 to the 60. So is that, what's that? 63? 64. But depends on sign or unsigned, right? Unsigned is larger. Signed. Yes. 63. Minus 1 for signed number. You plus sign. Signed number. So for unsigned, 64 minus 1. Yeah. 1 bit larger. Yeah. Things like that. Yeah. But it's very slow. Yeah. Yeah. You can think about if you calculate F92, you need to wait many minutes, quite a very long time. So you have to kill your program. Just 92. Yeah. All right? But later, we will find an efficient algorithm. You can even calculate F of 10,000, still in fraction of seconds. F of 10,000. Comparing with F of 92. 92. If you use brute force method, you need to wait many number of minutes. I don't know how long. Nobody has the patience to wait how long it is. But with another efficient algorithm, even if you calculate F of 10,000, they're large, just fraction of second. So the difference is huge. Yeah, so we need to study why the difference is so huge. Yeah. All right. Yeah. Yeah. So next, we need to understand the reason. Yeah. Here I just told you it is very slow, extremely slow. But what's the reason it is slow? Yeah. So we need to study. That's our next question. Here I want to draw a recursion tree to show you why it is slow. Now, we understand. What's the problem? Only after we understand where is the problem, then we can fix it. We remove that, that barrier, big barrier. Yeah. Then we fix the problem. So we can get an efficient algorithm. All right, here I want to draw a recursion tree. Use a relatively small Fibonacci number calculation, fiber of 6. That's a very small number, but you can already see the problem, the main problem, why it is so slow. In order to calculate fiber of 6, you need to know the value of fiber of 4 and the fiber of 5. Those two values, right? Yeah. So now, remember, I used the stack data structure to explain how to implement the, recursion in computer memory, right? Yeah. Fiber of 5, fiber of 4, both unknown, so we push them into the stack. Then do recursion, right? Yeah. All right. So you need to find the fiber of 5 value first, and fiber of 4 value first, before you can calculate fiber of 6. Now, all right. So you push these two numbers into the stack. All right. Then, in order to calculate fiber of 5, you need another round recursion, right? Fiber of 4, fiber of 3. Another round recursion. Here, also, another recursion. Yeah. And so on. Yeah? So, we do the recursion all the way down to the bottom. The bottom, because we need to reach the base case, then we can stop, right? So fiber of 1, fiber of 0, 1, 0. So when we reach the base case, then our recursion can stop. Yeah. So we can calculate. Right? All right. So from this recursion tree, do you see any special property? Yeah. That's a recursion tree. In order to calculate this small Fibonacci number, you need to do this much work. What's the problem here? Can you see something special here? Lauren? Yes, huge redundancy. Yeah. So here, because the same Fibonacci number, let us use F fiber of 2. it is repeated so many times. Look at that. So many times. Why you need to calculate the same Fibonacci number so many times? And this is a small Fibonacci number calculation. Think about if you do Fibonacci fiber of 100, you get a huge tree, right? Yeah. How much redundancy will you have when you calculate fiber of 100? Too much redundancy, overwhelming redundancy. Yeah. That's the reason it is slow. Yeah. Because based on our logic, each Fibonacci number should only be calculated once, right? If more than once, all redundant. So all the redundant calculation should be eliminated. Yeah. So that's our natural understanding. Yeah? But this brute force algorithm does not remove all the redundancy. Yeah. So that's the reason it is extremely slow. All right, then solution is pretty straightforward. Yeah? If I ask you to fix the problem, the idea is very simple. Yeah. You may not know how to do it, but the direction is clear, right? Direction is remove the redundancy. Then you improved. You improve the algorithm. Yeah. All right. Yeah. So next we will do that. We want to focus how to remove the redundancy. Yeah. All right. Yeah. Method 1. Yeah. Method 1, method 2. We have two methods we can use to improve redundancy. The method 1, we notice when we do the recursion, that causes the redundancy problem. How about we avoid recursion? Yeah? Because this recursive formula is so simple, we do not have to use the recursion to calculate Fibonacci numbers. We can use the iteration to calculate. The first method is very simple. So we use the iterative algorithm. Okay? Implementation also very simple. Yeah. Initialization, two initial values. Then one for loop. In this for loop, we do recursion. No recursive function call. Right? Yeah? Here, no recursive function call. Okay? Yeah, because every time when you calculate the current Fibonacci number, f of I, you use the previous two old values, and those two values are, they are already available. Because you calculate them before, all right? So this method we call the bottom-up method. Bottom-up. You calculate from bottom, from bottom to top. Yeah. So this is the bottom-up method. Okay, yeah. So the first one we can apply to remove the redundancy. No redundancy, right? No redundant calculation. Okay? Yeah. And this one is very fast. Yeah, so you can see it. Very fast. How fast it is. Yeah. How fast it is. Yeah. We have learned asymptotic notation, right? Yeah. If I ask you to use asymptotic notation to tell me how fast it is, can you apply asymptotic notation to tell me how fast it is? Yeah. If we use a big O notation, Big O of what? Big O of what? Can you see it? Big O of n. N. Yeah? Because how many in this for loop? Approximately n, right? N iterations. Yeah. Each iteration, one addition, right? Yeah. So n operations, n additions. Yeah. Basically n additions. So big O of n. Yeah. It's very fast. How about the previous one? Previous one, yeah. The brute force. If I ask you to use the asymptotic notation, how slow it is. Yeah, we want to use asymptotic notation to represent the brute force method. The previous one, right? Big O of not n factorial. yeah. But all right, yeah. Phi, yeah. So phi, what's that? Phi, golden ratio. Next, we will go to phi to the nth. It's an exponential function. It's an exponential function, but phi is a golden ratio. Yeah. Our next topic, we will learn golden ratio. Okay, it is closely related to the Fibonacci numbers. Yeah, it's a very important number, constant. Golden ratio, constant. Yeah, golden ratio. Yeah, here I can give you the number, the definition. 1 plus root 5 over 2. It's greater than 1. Yeah, so golden ratio number. All right, yeah. You can see, that slow, the brute force. Huge difference, right? Big O of n and the big O of phi to the n. A huge difference. Yeah. All right. Yeah. So that is the method 1. Now we want to look at the method 2. So the method 2, here we use bottom up. Method 2, we use top down. Okay? Yeah. So method 2, another interesting one. Yeah, but we need to study. Yeah. Another interesting idea. So recursive algorithm without redundant computation. Yeah. So here, method 2, we keep the recursive algorithm. This part. We keep it. We don't throw it away. Method 1, we throw away the recursive algorithm. No recursion here. Okay? So method 2, we keep the recursion. But we need to remove the redundancy. Here you can see this difference between method 1 and method 2. If we look at why we choose method 2, we have a good solution here. Yeah, so this solution is good. But why we consider method 2? There is an important reason. Because in our part A of module 3, we know recursive algorithm is powerful, right? So if we keep the recursive algorithm, we keep the power of recursion. That's very important. The first method 1, you do not use the recursion, then you cannot enjoy the power of recursion. So your problem solving capability will be very limited. Very limited, because you cannot use recursion, right? Too limited. For method 2, you can still use the recursion. Then your problem-solving method is not limited. Yeah, so you can use the strong power of recursion. Yeah, that's the important thing. So that's why we need to we cannot touch recursive algorithm usage. This point, we cannot touch it. We have to keep it. But we need to remove the redundancy. Yeah. All right. Question. How to do it? Yeah. How to do it? Yeah. So the idea. Use an array to store calculated values. That's the key idea. So this is the key idea. How to remove redundant? This is the key idea. Use an array. Yeah. So it's a temp array, right? Temporary array to store calculated intermediate. Okay. Intermediate calculated values. Do not throw away. Keep those intermediate calculated values because they could be useful later. So, that's the main idea. In this way, you can remove the redundancy. So we will see why. All right. Make sure that no value is calculated more than once. So why we can remove redundancy? Because this, make sure that no value is calculated more than once. Why you can make sure? Because you store the previously calculated values. You can check, okay? You can check your temporary storage. If those values you need are available or not. Okay? Just check it. Okay? If they are available, then no further calculation. If available, retrieve. Retrieve from the temporary storage. That idea. So you never need to calculate the same Fibonacci number more than once. Is that idea simple? Simple? Key value pair. Oh, yeah, talking about, but even simpler than that. Store in an array, right? Yeah. Right. Yeah, key value pair, so that's a good way. But here, because we can use array, simpler than that, right? Yeah? Because the array indices you use as the key. Yeah. So that way, actually, it has the same structure as key value pair, but the indices are used as the keys. So even faster, right? Even faster. Yeah. So the search very fast. All right? Yeah. So here. Yeah. Actually, this idea, it looks simple, right? So do you feel this idea looks simple? Yeah. But this idea is a very important problem-solving method. It's called a dynamic programming idea. Yeah. So this whole idea you have seen here, it's called a dynamic programming. It's a topic in chapter 8. Yeah. Actually, it's a graduate student topic. Yeah. But here, we need to use it. So I give you a short introduction. Dynamic programming. Yeah. This is dynamic programming. Yeah. So in our project number 2, so we will apply this algorithm. Dynamic programming. Yeah. All right. Then, so I need to explain a little more on this dynamic programming because the idea is so important. Yeah. So I want to use a little, just a little more time. All right. Dynamic. Okay. Yeah, your data again keeps changing. You are processing dynamic data. Okay. You are processing dynamic data. Yeah. Data comes in, in sequence. All right. Programming. So what's this meaning of programming? Yeah. The programming, the meaning here is not our, coding, that kind of programming. Yeah. So this is people use a very old meaning in computing history. Yeah. Computing history, the programming. Okay, what's the programming? The meaning. Yeah. Think about before computers are available. How to do programming before computers were available that time, right? Yeah. So people use hand to do calculation, to do so-called programming. All right. So what's the programming? Yeah. Yeah. You have no computer. You have no calculators. How do you do programming? Okay. At that time. All right. So people draw a table to organize data. So that process, they call it programming. Okay? Draw a table. Okay? Yeah. Arrange your data in a well-organized table. So then you do calculation. Based on that table, that's the programming. All right? Yeah. Here, dynamic programming refers to that meaning. Okay? Store your data in a table. That's dynamic programming, the meaning. Okay? All right. So you have a temporary storage. Yeah. Yeah. So people also call this method dictionary method. Dictionary method. Why dictionary method? Yeah. So the meaning also pretty intuitive. Yeah. Dictionary method. So you build a dictionary. You need to build your dictionary, to store your temporary data. Okay. Intermediate calculation results stored in a dictionary. And later you need to look up some of the numbers in your dictionary. So that's a dictionary method. Yeah. Yeah. So here you can see the meaning. Dictionary from this method. Dictionary, and from this program, people use a table. Yeah, the same thing. Dictionary and a table, the same thing. You use the table as the dictionary. Table, so you have rows, columns. Yeah, that's your dictionary. Yeah. Yeah. So you use the table as a dictionary. So you arrange your data, you store your data in a temporary table, but later you need to look it up. Okay? Yeah. In your table. All right. Then, regarding our using an array, so this array is our dictionary. We use an array, because our data is very simple. We don't need to use a table. So we use array as a special table. How about that? Okay? So array, we use as a dictionary. Okay? All right. So we have a sequence of locations corresponds to 0, 1, 2, 3, and so on. Okay? 0 we store f of 0. 1 we store f of 1. 2 we store f of 2. 3 we store f of 3. Okay? So we can store all the intermediate Fibonacci numbers in our temporary dictionary and array. Okay? Yeah. How do we use this dictionary? Yeah. Every time when you need to calculate one Fibonacci number, the first thing you need to look it up in the dictionary and see if it is available in the dictionary. If it is already available in the dictionary, don't do calculation. just retrieve it from the dictionary. That's very fast, right? You read it from the dictionary without calculation. Is it fast? That's fast. All right? Yeah. If it is not available, then you do calculation. In this way, you can guarantee you always calculate one particular Fibonacci number only once. Never more than once. That's the essence of dynamic programming. You always calculate the same number once. Never more than once. That's the essence of dynamic programming. Okay? Yeah. All right. Next, we can look at the solution. Yeah. Because we understand the idea, basic idea of dynamic programming. Now, implementation is very simple. Now, implement this idea. Yeah. Dictionary method. Yeah, very simple. All right. Yeah. Yeah. You know, yes. So here. Yeah. Okay. Yeah. All right. Now let's look at the pseudocode of implementation. Method 2, dynamic programming method. All right. Yeah. So here we use a dictionary method. Yeah. It's an array. So not a fancy dictionary. A very simple dictionary. Yeah. All right. Yeah. Yeah. So that's the the main points we use in our dynamic programming. Okay. All right. These 3 main points. Yeah. All right. Then the pseudocode. Yeah. 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 We need to do a little more work. Yeah. But the result is huge. Improvement is huge. Yeah. All right. So we initial integer variable s, temporary variable s, to store the temporary result. Yeah. First, this line, if, so here we create our dictionary, we call the known f. Yeah, from the name, we want to use this dictionary to tell us if the Fibonacci numbers are known or not. So known f. Yeah. So how to define known or not? If known f of I value greater than 0, then it's known. Known Fibonacci. Because we initialize this array, known f array, initialize to 0. Okay? Well, yeah, because by default, yeah. So, yeah, initialized to 0. Yeah. Initial value is all 0. So if it's non-zero, greater than 0, then that means you already calculate the corresponding Fibonacci number before. That's the reason it is non-zero. It's greater than 0. So this is the checking step. Okay? Yeah. Here we use index I. Yeah. So Jeremy said the key value pair. Yeah. Here, what's the key? Index I is the key. We use index I as the key to search, to find its value, and then we compare the value there with 0. If it's greater than 0, then return it. Don't do calculation. Just return, to the stack, right? Yeah. Because you need to find this value, return it, then it's available in the stack, then you can use this known value to do the calculation. Yeah. All right. So after that, 2 base cases, 0, 1. Then recursion, you stop. So after you do the recursive function call, yeah, fiber of I minus 1, fiber of I minus 2, you store it in S temporary variable. Yeah. All right. Then before you return S, you assign it to known f of I. You update it. Yeah. Because in location I, known f value is 0. Because after you get down, all right, so, yeah, because if it's non-zero, you return. You do not go down, go lower, right? Yeah. So when you get to these lines, that means that already it means the known f of I must be 0. Then you can get down, right? Yeah. Otherwise, you bounce back, right? If it's greater than 0, then after this line, bounce back. But if you can pass this line, known f of I must be 0. Okay? Yeah. So that's why the return line, the last line before return, you assign s to this to change the 0 value to be s. Okay? Yeah. To update it, update your dictionary. Okay? Yeah. Update your dictionary. Yeah. For future usage. So this value will be used in the future. Yeah. So this is the dynamic program. In this way, so you can keep the recursion, but at the same time, you remove the redundancy. Redundancy is gone. Okay? Yeah. So that's the method 2, dynamic. So this method, this dynamic programming, this method, we call it top-down. Top-down method. Yeah? Because you start from top, right? Yeah. So when you do recursion, so you start from top. Fiber of n, you enter n. So then, inside you do the top down. Okay? Yeah. 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 So that's top down. Yeah. The previous one, method 1, bottom up, top down. Yeah. These two different methods. Yeah. All right. Yeah. So we complete the calculation part. Yeah. All right. C.2, golden ratio. This time, we need to, study our second approach. We need to find a math formula to do calculation. That's even faster than this big O of n method. Even faster than that. Yeah. All right. First, what's the golden ratio? So why, people gave it a nice name. Yeah. Golden here means important, right? If it's not important, so people won't call it a golden ratio. Yeah. If something useless, so people won't call it a golden something. Yeah. So it's very important. Yeah. So here, so let's look at. Yeah, I remember I borrowed a book from library before. Yeah, a small booklet. Yeah. So the whole booklet talking about golden ratio story. A lot of nice, beautiful properties, usages. Yeah. So here just related to painting. Yeah. Da Vinci's painting Mona Lisa, the very famous one, and some people argue related to the golden ratio and the Fibonacci number. Yeah. So the position things. Yeah. So here you can see some nice properties. So first, related to Fibonacci numbers. Yeah, let's look at Fibonacci number. Fibonacci f of 0 equals 0. So this one is not used because 0, nothing, right? So after that, yeah, f of 1. Yeah, so f of 1 equals 1. F of 2 also equals 1. Okay, 2, 1. So then you draw a square with the side 1. Yeah. The side is Fibonacci number. Okay, 1. Then another one, f of 2. Yeah, 2 unit squares. So you align them. Yeah. So this you get a rectangle, right? Yeah. After alignment, you get a rectangle. Then f of 3, yeah, this too is f of 3. You can see f of 3, you can also place it in a appropriately, so you get a nice rectangle here. Okay? F of 4 equals 3, yeah, so you get another, nice rectangle. F of 5, keep doing, so you always get a rectangle. Yeah, perfect rectangle. Okay, yeah, all right. And this rectangle, so you can draw a quarter arc. Yeah, so when you have a square with one of the vertices as the center, you can draw a circle, right? But here you just draw quarter circle. So it is an arc. Yeah. So each square you draw a quarter, this arc. So here you can see this one you draw arc like this arc. This here arc. Yeah. So there you can get a this nice spiral curve. Yeah, nice spiral curve like that. Okay, yeah. So here, yeah. So so with all those beautiful properties, yeah. So that's the reason people call it a golden ratio. Yeah. But we need to see what is the specific number of golden ratio. Here you describe, something using Fibonacci numbers, Yeah. What's the real golden ratio number? Yeah. So there is another story. So we want to look at it, the golden ratio, how to derive it. Yeah. So here we use line segments to help us get an idea of this golden ratio story. Okay, all right. Yeah. Because at the ancient time, people studied the numbers at ancient time. Yeah. They know numbers are very useful. Okay? Yeah. And they try to understand the universe using numbers. Yeah. All right? Yeah. Yeah. So then, some people argue, so how to define some special number? Yeah. So they want to find a number very special, very interesting number, not a plain trivial number. Okay? Yeah. So that number has some special property. So some people make story using two line segments. The first line segment with length A, second line segment with length B. Then you join these two line segments, so you get a longer line segment. Yeah. All right. Then they make this argument. Yeah. The goal is they want to build a special number through some interesting story. Okay? Yeah. So that's the goal. All right. So how to define that special number? Yeah. One longer line segment, one shorter. So you take the ratio, so that ratio should be greater than 1, right? So if you look at A over B ratio, you know this number should be greater than 1. Okay? Yeah. So you have this in your mind, then from the picture here, from the diagram here, you want to find another ratio that is greater than 1. Then you want to connect these two ratios. Yeah. So you use the line segments that appear in this diagram, yeah, and to get a ratio that is greater than 1. So how to get that? So another possibility is longer line segment A plus B. Yeah? The sum of the length of these two line segments A plus B over A over the longer one, yeah, you know, both of these ratios, these two ratios are greater than 1, but people want to see under what condition these two ratios are the same. That's a special property, right? Yeah? Yeah. Only under a very special situation, they are the same. In general, they are different. In general, they are different. Yeah. But only there is one special A over B ratio. When that happens, they are the same. Yeah. But what is the real number here for the ratio? Okay? Yeah. So let's find the answer. Yeah. Yeah. So after the story that people describe the special ratio, then we need to find a solution. Yeah. All right. To find a solution, first let's simplify the A plus B over A fraction to get a 1 plus B over A. Yeah? Yeah, so the integer part is 1. B over A smaller than 1, yeah, because B is smaller than A. Yeah. So it is 1 plus something. Yeah. Yeah. A over B equals 1 plus B over A. Can we find A over B? Yeah. So that's the question. Yeah. To answer this question, yeah, so the obvious method is we introduce a new variable x. Yeah. Let's make A over B equal to x. Yeah. One variable, yeah, because A over B, there are two unknowns, right? A unknown, B unknown. Yeah. After we replace this ratio by x, we only have one unknown, x. Yeah. So that's much easier. Yeah. All right. So after we introduce this new variable x, then can you see B over A equals 1 over x? Reciprocal of x. Yeah, because you flip top down, bottom up, you just flip numerator, denominator. That's the reciprocal operation. So that is 1 over x. So your new equation becomes x equals 1 plus 1 over x. Is it very simple? Yeah. So you get a one variable equation. Should people have the confidence to solve it? Yeah. The solution. All right, let's look at the solution. To find solution, let us remove the denominator, so we get an x squared equals x plus 1. So it is a quadratic equation. Quadratic equation. Yeah. Yeah. All right. So we can solve this quadratic equation by the quadratic formula. Okay? Yeah. So let's solve this quadratic equation by the quadratic formula. Yeah. Quadratic formula, we apply it on the standard quadratic equation. A x squared plus bx plus c equals 0, but a cannot be 0. Yeah. Then we have the quadratic formula. So x equals, there are two possible solutions. Yeah. So negative b plus minus root of b squared minus 4ac, then the whole thing over 2a. That's the quadratic formula. Yeah. Now we apply it to our special quadratic equation. Yeah. So we have a equals 1, b negative 1, c negative 1. So let's plug in. All right. So by the quadratic formula, we have x equals two possible values, 1 plus minus root 5 over 2. Yeah. So this x represents a over b. It's a ratio, a over b ratio. Yeah. So can we, yeah, because we know two possible values. Another value here is the 1 minus root 5 over 2. It's negative. we can see it's a negative number. Negative number, but the x equals a over b must be positive, right? Yeah. X must be positive. So it cannot be negative. So the negative value is drop it. Yeah. So that's why we have two possible values, but the negative one does not make sense in our story, right? In our story. Yeah. It does not make sense. So we drop it. So we keep the positive value, 1 plus root of 5 over 2. Yeah. So this number, people call it golden ratio. That's the golden ratio, right? Yeah. So then, similar to pi, yeah, because the pi is a famous constant. So here people use a special Greek alphabet, phi, to represent golden ratio. So everybody uses phi to represent the golden ratio. Okay? Yeah. All right. Yeah. So next time we will use the golden ratio to find Fibonacci formulas.